Right now, as you're watching this, your car is doing something almost miraculous. Inside that engine, thousands of controlled explosions are firing every single minute. Pistons are slamming up and down with enough force to crush bone. Metal components are spinning at speeds that generate temperatures hot enough to cook food. And all of it, every single violent, chaotic process happening under that hood, is being kept in perfect, precise balance by engineering so well designed that most of us never think about it once. We just turn the key, we drive, we assume it'll work tomorrow the same way it worked today. And for most people, that assumption holds right up until the day it doesn't. Because here's what nobody tells you. The most expensive car damage in the world doesn't come from crashes. It doesn't come from obvious neglect. It comes from 5 completely ordinary habits that millions of drivers repeat every single day, completely unaware that each one is chipping away at a precision machine built on tolerances measured in thousandths of an inch. No warning lights, no unusual sounds, no drama, just invisible damage, compounding quietly over months and years, until one day you're sitting in a mechanic's waiting room and someone walks out holding an estimate that genuinely makes you feel ill. Today we're going inside the physics. We're going to understand not just what these mistakes are, but why they're so destructive. What's actually happening at a mechanical and physical level the moment you make them. Because once you understand the engineering, these aren't just tips to remember. They become things you can never unsee. Let's start from the beginning. To understand why these 5 mistakes are so dangerous, you first need to understand something fundamental about how modern cars actually work. Most people think of a car as a robust, durable machine. And on the surface, that's true. Cars are built to handle heat, friction, vibration, and stress day after day for years. But that durability isn't unconditional. It exists within a very specific set of operating parameters. Precise ranges of temperature, pressure, lubrication, and force that the entire system is engineered around. Step outside those parameters, even slightly, even briefly, and something interesting happens. The damage doesn't appear immediately. There's no sudden failure. Instead, the machine absorbs the insult at a microscopic level. A bearing surface gets a little rougher. A rotor develops a tiny, uneven spot. A transmission clutch pack loses a fraction of its material. You feel nothing. You hear nothing. The car keeps driving, but the damage is real. And it compounds. Every subsequent time you repeat the same mistake, the already compromised component takes another hit. The rough bearing gets rougher. The warped rotor warps a little more. The worn clutch pack absorbs a little less shock than it did before. Engineers call this cumulative fatigue. Materials. Scientists call it stress cycling. Mechanics call it the reason they can afford nice things. This pattern, invisible stress, silent accumulation, sudden catastrophic failure, isn't new to engineering. In the early days of the automobile, engineers discovered it the hard way, over and over again. Early engines running without pressurized lubrication systems seized on long road trips because nobody understood what oil deprivation did at the molecular level. Early drum brakes failed catastrophically on mountain descents because nobody had fully modeled what repeated heat cycling did to metal. Early rigid axle designs snapped on rough roads because the relationship between speed, impact force, and material fatigue wasn't yet understood. We solved every one of those problems, but solving them required understanding the physics deeply enough to design around it. The 5 mistakes we're about to cover essentially undo that engineering. They recreate those same failure conditions inside vehicles that were specifically built to avoid them. Mistake 1. Driving with low engine oil. Let's start with the one that kills engines fastest because the physics here is more surprising than most people expect. Ask someone what engine oil does and they'll say it lubricates things. It keeps parts from grinding together, and that's true. But it's maybe 40% of the full picture. Engine oil is actually doing 3 distinct critical jobs simultaneously, and losing enough of it compromises all 3 at once. Job 1 is lubrication. Inside your engine, metal components are moving at extraordinary speeds. The crankshaft, connecting rods, and camshaft don't just rotate. They rotate fast. At highway speed, engine bearings are spinning over 100 times per second. At those speeds, the goal isn't to reduce friction, it's to eliminate contact entirely. Under normal operating conditions with sufficient oil, moving parts never actually touch each other. They're separated by a pressurized film of oil just a few microns thick and thinner than a human hair. The parts are essentially flying above each other on a cushion of liquid. Remove enough oils and that film collapses. Metal contacts metal, and this is where the physics gets genuinely alarming. At the speeds involved, metal-to-metal contact doesn't just cause wear. It causes a phenomenon called adhesive wear, sometimes called microwelding. The asperities, the microscopic peaks on each metal surface, contact each other with enough pressure and heat to momentarily fuse. Then they're torn apart by the motion. Then they fuse again, thousands of times per second. Each cycle leaves both surfaces slightly more damaged than before. Job 2 is thermal management. This surprises most people. Engine oil removes up to 40% of the engine's heat. Your coolant system gets most of the attention, but oil is circulating through areas of the engine that coolant never reaches. Around bearings, through oil galleries in the crankshaft, across the underside of pistons. When oil level drops, thermal management in those areas drops with it. Components that were running at their design temperature begin running hotter, and higher temperatures accelerate every other failure mode simultaneously. Job 3 is keeping the engine clean. Oil suspends combustion byproducts, metal particles, and contaminants and carries them to the filter. Low oil means a higher concentration of those contaminants in whatever oil remains, and those particles become abrasive agents circulating through your engine. The combined result of losing even 1 quart of oil is a system running hotter, dirtier, and with compromised lubrication, all at the same time. Studies have shown that an engine running significantly low on oil can suffer irreversible bearing damage in under 30 minutes of highway driving. The eventual failure, a spun bearing, a seized engine, can cost anywhere from $4,000 to $12,000 to repair, for the cost of a quart of oil in 30 seconds of checking the dipstick. Mistake 2, slamming the brakes constantly. Here's something that reframes how you think about your braking system. Your brakes are not primarily friction devices. They're heat machines. Their entire job is to convert your vehicle's kinetic energy, inert, the energy of motion, into thermal energy, meaning heat. Every time you brake, you are deliberately generating enormous amounts of heat as fast as possible, and then getting rid of it. The engineering challenge is controlling that heat, and understanding that challenge explains exactly why aggressive braking is so destructive. When you brake hard from highway speed, the brake pads clamp against the rotors with significant force. The friction between pad and rotor generates heat almost instantaneously. At 70 miles per hour, a hard stop can raise rotor surface temperatures above 500 degrees Fahrenheit within seconds. In extreme performance driving or repeated hard stops, think descending a long mountain grade, rotor temperatures can exceed 1,000 degrees Fahrenheit. At those temperatures, something happens to the metal that the rotor was never designed to handle repeatedly. Thermal expansion. Metal expands when heated. It contracts when cooled. A rotor that heats unevenly, which happens under hard braking because the pad contact zone heats faster than the rest of the rotor and expands unevenly. Then, when you release the brakes and the rotor cools, it contracts unevenly. Do this repeatedly, and you've introduced internal stress patterns into the metal that permanently alter its geometry. The rotor warps. The surface that was once perfectly flat and parallel now has high and low spots. Every time the warped surface contacts the brake pad, it creates a pulsation, that familiar shuddering you feel through the brake pedal when braking from speed. But it's not just annoying. A warped rotor reduces braking efficiency because the pad can't maintain consistent contact across the entire surface. And a rotor under ongoing thermal stress is a rotor with a shortened service life. The historical context here is vivid. Before disc brakes became standard, vehicles used enclosed drum brakes. Drum brakes are terrible at heat dissipation. The heat is trapped inside the drum with no airflow. On steep mountain roads in the mid-20th century, repeated braking on long descents would superheat drum brakes to the point of brake fade, a condition where the braking surfaces become so hot that friction effectively disappears. Drivers would press the pedal and feel almost no resistance. People died because of this. Disc brakes, vented rotors, and high-temperature brake compounds were all developed specifically to solve this heat problem. Aggressive, repeated hard braking undermines those solutions. The fix is simple. Anticipate stops earlier, brake progressively and smoothly, and give your rotors time to dissipate heat between applications. Mistake 3. Hitting potholes at speed. The physics of pothole impacts is genuinely shocking once you understand it, because most drivers dramatically underestimate what's actually happening. When your wheel drops into a pothole, the sequence of events is fast and violent. The wheel falls into the void, then strikes the far edge of the pothole as it tries to climb back out. That impact sends a force pulse, a shock wave, up through the tire, into the wheel, and then through your entire suspension system, nearly instantaneously. Wheel bearings, tie rods, ball joints, control arms, steering knuckles, and your vehicle's alignment geometry all absorb that pulse simultaneously. Now here's the physics that makes speed so critical. Impact force doesn't scale linearly with speed. It scales with the square velocity. That means hitting a pothole at 50 miles per hour doesn't generate twice the force of hitting it at 25. It generates roughly 4 times the force. The difference between a slow crawl and highway speed isn't a factor of 2 or 3 in terms of impact force. It's closer to a factor of 6 or more. Studies have shown that pothole impacts at significant speed can generate several tons of force through the wheel assembly in a fraction of a second. Consider what those several tons of force are hitting. Your wheel bearings are precision machine assemblies with balls or rollers running in hardened steel races. They're designed to handle the steady, rolling load of the vehicle's weight. They're not designed to handle sudden lateral and axial shock loads. Ball joints and tie rods are load-bearing links in your steering and suspension geometry. They handle constant, predictable forces well, but shock loads can deform or crack them. Worst of all, alignment, which the precise angles at which your wheels contact the road, can shift from a single severe impact, and misaligned wheels create uneven tire wear that compounds silently over thousands of miles. Early automobiles with rigid, unsprung axles and minimal cushioning made this problem glaringly obvious. A bad road impact could literally snap a wooden spoke wheel or bend a solid steel axle. The sophistication of modern suspension systems, multi-link geometry, hydraulic dampers, compliance bushings, was developed specifically to absorb and redirect these forces. But the physics of the force is the same. Modern suspension absorbs it more gracefully. It doesn't make it disappear. Mistake 4. Ignoring tire pressure. Tires are one of the most sophisticated components on your vehicle, and also one of the most misunderstood. Most people think of them as rubber donuts filled with air, but a modern tire is an engineered pressure vessel, a precisely constructed composite structure of rubber compounds, textile plies, and steel belts that works correctly only within a specific pressure range. Outside that range, physics takes over in ways that are invisible until they're catastrophic. Here's what happens inside an underinflated tire. The tire's job is to support the vehicle's weight and transmit driving, braking, and cornering forces to the road surface. With correct inflation, the air pressure distributes that load evenly across the entire contact patch and through the tire structure. The sidewalls flex only slightly with each rotation, a small, controlled deformation that the tire is designed to handle indefinitely. Drop the pressure and the load distribution changes. The sidewalls, now unsupported by sufficient air pressure, flex significantly more with each rotation. At highway speed, a tire rotates roughly 800 times per mile. Each rotation is a flex cycle. Each flex cycle generates heat through hysteresis, the energy loss as rubber repeatedly deforms and recovers. More flex, more heat, faster degradation of the internal structure. And here's the critical detail. The damage happens to the internal cords, the layers of polyester or nylon textile that give the tire its structural integrity. Long before anything is visible on the outside, the tire can look perfectly normal while its internal architecture is being progressively destroyed by heat fatigue. When those internal cords fail, the tire doesn't slowly deflate. It blows out, potentially at highway speed. The same pressure vessel principle explains why a properly inflated aluminum soda can is nearly impossible to crush with your hand, but a slightly dented or partially empty one collapses easily. The structure depends on an internal pressure to maintain its integrity. Your tire is doing the same thing at 70 miles per hour, supporting a vehicle that weighs thousands of pounds. Mistake 5. Shifting before a full stop. Of all 5 mistakes, this one generates the most disbelief when people first hear about it because it feels so minor. You're rolling backward in a parking lot, almost stopped, and you shift to drive to pull forward. What's the harm? The harm is inside your transmission, and it's more violent than you can imagine from the outside. Automatic transmissions are remarkably complex devices. Inside, they contain clutch packs, sets of friction plates and steel plates alternately stacked and squeezed together by hydraulic pressure to engage different gear ratios. They contain planetary gear sets, intricate arrangements of sun gears, planet gears, and ring gears that manage torque multiplication and direction of rotation. All of it operates under hydraulic pressure, controlled by a sophisticated valve body that manages fluid routing with extraordinary precision. When you shift from reverse to drive while the vehicle is still moving backward, Here's what the transmission is being asked to do. The output shaft, connected to your wheels and therefore still rotating in the reverse direction, is suddenly told to rotate in the forward direction. The clutch packs that control forward drive engagement are slammed together under full hydraulic pressure while the opposing momentum is still present. This is torque shock. The clutch friction surfaces absorb the entire momentum difference in a fraction of a second. The heat generated in that instant burns and glazes the friction material. The steel reaction plates absorb shock loads they were not designed to handle repeatedly. Over time, the friction material wears away faster than it should. The clutch pack loses its ability to engage cleanly. Slipping begins. And slipping generates more heat, and more heat accelerates wear. The system enters a death spiral. One damaged clutch pack can also contaminate the entire transmission fluid system with burnt friction material particles, and those particles circulate through every other component. A transmission rebuild averages thousands of dollars. And the insidious part is that automatic transmissions hide this violence from the driver. In a manual transmission, you would feel and hear exactly what's happening. In an automatic, you feel nothing until the transmission begins to slip, and by then, the damage has been accumulating for years. What makes these 5 problems so fascinating from an engineering standpoint is that none of them are unique to automobiles. Every single physical principle at work here appears constantly in other areas of your life. Once you see these patterns, you start recognizing them everywhere. Oil starvation is just a specific case of lubrication failure. The same problem that seizes bicycle chains, burns out ceiling fan motors, destroys air conditioning compressors, and wears out sewing machine gears. Anywhere mechanical components move against each other at speed, that lubricating film is the only thing preventing direct contact. The machine's lifespan and the lubricant's presence are essentially the same variable. Brake heat shock is the same mechanism that cracks cast iron skillets when you move them from a hot burner to a cold surface too quickly. It's the same phenomenon that causes railway wheels to develop flat spots under repeated heavy braking. It's why thermal shock testing is the standard quality control procedure for any material that will experience rapid temperature swings. Rapid temperature differential creates internal stress. Materials have finite tolerance for this stress. Exceed it enough times and they fail. Pothole force physics is identical to the engineering challenge your running shoes are solving. The cushioned midsole in a well-designed running shoe exists specifically to reduce peak impact force transmitted to your joints. The same joints that, without cushioning, would sustain cumulative stress fractures from thousands of foot strikes. Mountain bike suspension forks, washing machine drum mounts, earthquake damping foundations under buildings, all of them are managing the same fundamental problem: sudden, violent impulse forces that need to be absorbed, redirected, and dissipated before they reach something that can't handle them. Tire pressure mechanics mirror the structural engineering of any pressurized vessel. A properly inflated tire, like a properly pressurized scuba tank or aircraft fuselage, distributes external loads across its entire surface through internal pressure. The structural integrity isn't in the shell alone. It's in the combination of shell and internal pressure working together. Remove the pressure, and the shell is suddenly trying to do a job it wasn't designed to do alone. And transmission torque shock is something you felt viscerally if you've ever accidentally tried to reverse an electric drill while the bit is still spinning or jammed a blender into reverse mid-cycle. Industrial conveyor systems have entire engineering sub-disciplines dedicated to managing motor reversal under load. The physics is the same whether you're reversing a transmission or a drill motor. You're demanding instantaneous momentum reversal from mechanical components, and those components have to absorb the energy of that reversal somewhere. It's worth being honest about something. None of the solutions here are perfect. Every engineering compromise in your car was made for a reason, and understanding those trade-offs helps you make smarter decisions rather than just following rules blindly. High-performance braking is a perfect example. Harder braking genuinely does stop you faster. The physics is real. Racing vehicles use enormous ventilated multi-piston brake systems specifically to manage the heat that aggressive braking generates. They've engineered around the problem rather than avoiding it. The trade-off on a standard passenger vehicle is between maximum theoretical stopping power and rotor and pad longevity. Progressive anticipatory braking preserves your components. It does not make you safer in a true emergency. Stop. In that situation, brake as hard as necessary and sort out the rotors later. Tire width and profile is another genuine trade-off. Lower profile, wider tires improve handling response, and cornering grip substantially. They're also significantly more vulnerable to pothole damage precisely because the reduced sidewall height means less rubber to absorb impact before the wheel contacts the road surface. You're trading ride comfort and impact resilience for performance. Neither choice is wrong, but it's worth knowing what you're trading. Automatic transmissions hiding their own abuse is perhaps the most interesting design tension. The smoothness and simplicity that makes automatic so pleasant to drive is partly achieved by dampening driver feedback. In a manual transmission, bad technique creates immediate, obvious, unpleasant sensations. The driver learns. An automatic absorbs those mistakes silently and stores the consequences for later. That's a feature that became a hidden cost. Even oil change intervals have nuance. The old universal guideline of every 3,000 miles was established in an era of conventional motor oils and engines with far looser tolerances than modern units. Today's full synthetic oils in modern engines are typically rated for significantly longer intervals between changes, depending on manufacturer specifications, driving conditions, and oil quality. The principle that oil degrades and must be replaced is unchanged. The specific interval varies dramatically. Check your owner's manual, not folklore. Your car is not fragile. It is an extraordinary piece of engineering. A machine that manages heat, pressure, lubrication, and mechanical force simultaneously, thousands of times per minute for years on end. That's genuinely remarkable. The people who designed it were solving hard problems with elegant solutions. But elegant solutions have boundaries, and the 5 mistakes we covered today don't just approach those boundaries. They specifically recreate the failure conditions that the engineering was designed to prevent. Low oil eliminates the film that keeps metal from touching metal. Aggressive braking creates heat cycling that warps precision machine surfaces. Pothole impacts at speed generate force levels that shock load components built for steady stress. Wrong tire pressure converts an engineered pressure vessel into a flexing heat generating failure waiting to happen. And shifting too fast asks your transmission to reverse momentum in a fraction of a second, burning through components that were never designed for that load. None of these failures announce themselves. That's what makes them so costly when they finally arrive. But now you understand the physics behind each one. You know what's actually happening inside your engine, your brakes, your tires, and your transmission in the moments these mistakes occur. You understand why the damage is real, even when it's invisible. That knowledge changes how you drive. Not because you're following rules, but because you can picture the lubrication film collapsing, the rotor temperature spiking, the torque shock slamming through the clutch pack. You're not just a driver anymore. You're someone who understands what's happening inside the machine. And once you see the physics, it's everywhere. In your bicycle chain, in your running shoes, in the soda can in your hand, in the brakes on a freight train descending a mountain pass. The world is full of systems managing invisible forces. Your car is just the one you trust your life to every day. Take care of it accordingly.